Hi everyone, this is my physics 4 lab. So the purpose of this lab was to observe the motion of a mass oscillating vertically on a spring, and we were able to compare the predicted motion and the observed motion of the mass. And by the end of the lab, the law of conservation of energy was proven, and the system's total energy remained conserved. Some details are that the system was the mass. The observed motion graph, we used tracker, and for the predicted motion graph, we used GlowScript. So some conditions and connotations of the lab is the initial position was negative 1.401 meters in the y direction. The K value was 6.0922. The mass of the block was 0.402 grams. L naught was 0.0533. And we stretched the spring and released it, and we started the time while the object was already in motion and used tracker to get the positions of the oscillation. So the first principle that I'll be talking about is Newton's second law, which states that the system's change in momentum is proportional to the force added. The first formula shown is the net force of the spring, which is the spring force plus the force of gravity, and this is necessary since the spring also points in the y direction. The position and velocity update formulas were also needed, and for the energy principle, this means that the change in energy is equal to work plus thermal energy, and some other important equations that we use were the kinetic energy formula, the change in gravitational potential energy, and the change in spring potential energy. And then finally we used Hooke's law, which was able to help us find the spring stiffness through that. So shown here is the tracker data, which I converted into a CSV to input that into GlowScript and into the GlowScript code. So tracker was able to make the graph shown right there, which shows the position in the X and the Y direction. And so this is the code for the initial conditions. So the mass, the ball, as we said, 0.402, initial position in the X was negative 8.8, E negative 2, and in the Y, negative 0.66, and the gravity constant 9.8. Spring constant we found was 6.83, and this was found using that formula, T squared equal to 4 pi squared times mass over stiffness, and then arrange that to get the stiffness, and then L naught, which was 0.123, which we used the spring force formula. So we found that L is equal to the ball position minus the spring position, and L hat is equal to L divided by the magnitude of the length, and S is equal to the magnitude of L minus L naught. And moving to the energies, the system's energies, the kinetic energy was equal to 1/2 times the mass times the magnitude squared, and the UG is equal to the mass times gravity times the position in the y direction. The spring potential energy was equal to 1/2 times the spring constant times S squared, and then the total energy is just the kinetic, gravitational, and spring potential energies added up. So finally, the spring length and system energy, the gravitational net force is negative mass times the gravity in the y direction. The spring net force on the mass is spring equal to the spring constant times S times L hat, and the net force is the spring force plus the gravitational force. And to calculate the energy changes, the kinetic, gravitational potential, and spring potential energies are the same formulas as below. And to get the change in each one, you just subtract the final form from the initial. And then finally, to get the change in energy, you just subtract the final energy from the initial. So here are the graphs generated by tracker. And the first graph shows the change in energy versus time. And then the next two graphs on the right shows the X and Y positions versus time. And as you can see, the graphs are very similar, but as you can see, the experimental model is kind of off, and that's due to some errors, which could have been through tracking the center of mass on tracker, or it's possible that there was other external forces that weren't taken account of when we were calculating the forces involved in the experiment. So what does this mean? So to answer the first question, is the energy principle satisfied? It was satisfied since the delta E is 0 and the total energy is conserved. But even though there were different energies present in the graph, it shows that the total change in energy was 0. So for the next question, you can see the stiffness in each direction was different in the X and Y direction, which means that the direction will affect the spring constants and the graph. So the k that we found was different in the y and the x direction. Thank you.